In this video, we'll look at a technique to create a linear model for a relationship between two quantitative variables, and use this model to make predictions about the values of the variables. In previous videos, we considered the percent of deaths in each country that are caused by indoor air pollution, and explored some variables that could be related to this percentage. We focused at first on the percent of the population of each country with access to clean cooking fuel. We made a scatter plot to examine potential relationships between these two variables. We noticed a pattern in the scatter plot, a negative linear association, which meant that as the percent of population with access to clean cooking fuel increases, the percent of deaths caused by indoor air pollution decreases. Our goal is to use the values of one variable to make predictions about the other variable, that is, to use the clean cooking fuel access to predict the death rate. In order to do that, we need to create a model for this association. Since the relationship is linear, we can try to model it using the equation for a line. In this generic model, b1 is the slope and b0 is the intercept. After we compute the values of these coefficients, we'll interpret them in the context of the situation. The line we create from our model should essentially minimize the overall distance between itself, the line, and the data points. We'll use a computer to construct the line, which has a slope of negative 0.1324 and an intercept of 13.1052. Let's interpret what these coefficients are telling us. Here, we are using the percent of population with access to clean cooking fuel as the predictor variable, and the percent of deaths caused by indoor air pollution as the outcome variable. In this scenario, the intercept means that in a country where nobody has access to clean cooking fuel, 13.1052% of deaths are caused by indoor air pollution. The slope means that for each increase in clean fuel access, written as delta x, the indoor pollution death rate decreases proportionately by 0.1324 times as much as delta x. So, for example, this model is saying that in a country where nobody has access to clean cooking fuel, then just over 13% of deaths should be caused by indoor air pollution. And if we increase the clean fuel access rate by, say, 25 percentage points, would predict that the percent of deaths from indoor air pollution would decrease by 25 times 0.1324. And if we increase the clean fuel access rate again, we'd predict a corresponding drop in the percent of deaths. And we could make these predictions for each of the countries. But if we look at the actual data points, it's pretty clear that not every country has data values that lie on this line. To indicate that our model is only producing estimates, we write a hat on top of the y. These estimates allow us to make predictions, so they're still useful even if the predictions aren't perfectly accurate. Now, we can create a more complete model, one that accounts for the errors in our predictions. To do this, let's think about these errors. For example, if we look at the data for, say, Nepal, the length of this red line shows the size of the error in our prediction. That is, our model predicted that the percent of deaths caused by indoor air pollution in Nepal would be 9.45%, but it was actually 13.02%. The difference between the actual and predicted values is called the residual, and in this case it's equal to 3.57%. We can incorporate this residual into our model, so we can compute the actual value for Nepal using our prediction model plus the residual. And now we should also consider the residuals for all of the other countries. To represent all of the countries in our model, we'd write y sub I to represent the computation for each country, and e sub I to represent the residual, or error, for each country. So in general, we can think of our model as saying that the actual values in our data can be thought of as the fit of our prediction model plus the residual, or error, in our prediction. Now I'll summarize what we've seen here. In this video, you saw how to create models to make predictions about data values. Our methods only work when there is a linear association between the predictor and outcome variables. We created a model to predict the values of the outcome variable, y, using the predictor variable, x. Our predictions weren't perfect, so we labeled the predicted values y hat. We interpreted the meaning of the coefficients, specifically the slope, b1, told us that if x increases by delta x, then y increases by b1 times delta x. And the intercept, b0, is the value of y when x is equal to 0. The difference between the actual and predicted values is the amount of error in our predictions, and we called this residuals. Finally, we thought about a full model, which we could write as the actual data values are equal to the fit of our prediction line plus the residual or error in our prediction. And we could write this in our notation as y sub I is equal to b1 x sub I plus b0 plus e sub I.